For most of human history, we looked up at the night sky and wondered if there were other worlds out there. We didn't know we had theories. We had hope. We had mathematics that suggested it might be possible. But we didn't know. It wasn't until 1992 that we confirmed the first planets orbiting a star beyond our sun. Not around a normal star, but around a pulsar, a dead star spinning hundreds of times per second, shooting beams of radiation into space. That should have been our first warning. Since then, we found thousands of exoplanets, thousands of worlds scattered across the galaxy. We found them using methods that sound like science fiction. We watch stars for the tiny dimming that happens when a planet passes in front of them. We measure the wobble in a star's motion caused by a planet's gravity. We analyze the light filtering through alien atmospheres. And what we've learned is this: the planets we grew up with are not the template. They are not the standard. They are barely even common. The universe has been making planets for billions of years, and it turns out most of them don't look like anything we recognize. When you think of a planet, you think of something solid, something with a surface you could theoretically stand on even if it would kill you. Maybe an atmosphere, maybe water. You think of Mars with its red deserts, Venus with its crushing clouds, Earth with its oceans. You think of Jupiter's stripes or Saturn's rings. These are the images burned into your mind from textbooks and documentaries. But the universe doesn't care what you think a planet should be. Let me show you what we found. There's a planet called HD 189733b. It's about 64 light years away in the constellation Vulpecula, a gas giant roughly the size of Jupiter. At first glance through our telescopes, it looks almost beautiful. Deep cobalt blue, like Earth from space, like something peaceful. But it is not like Earth. The blue color comes from silicate particles suspended in its atmosphere. Glass. Tiny particles of glass scattering blue light. The planet is so close to its star that it completes an orbit in just 2.2 Earth days. Surface temperatures exceed 1,700 degrees Fahrenheit. Winds scream across the planet at over 5,000 miles per hour, 7 times the speed of sound. Faster than any hurricane that has ever existed on Earth. And in those winds, molten glass condenses. It rains glass sideways, horizontal sheets of it driven by supersonic winds. Shards of silicon dioxide tumbling through an atmosphere thick with vaporized sodium and vaporized iron. If you could somehow stand there protected from the heat, you wouldn't burn first. You wouldn't suffocate first. You'd be flayed by glass moving faster than bullets. That's not a metaphor. That's what the atmospheric models tell us. That's atmospheric science. HD 189733b belongs to a class of planets we call hot Jupiters. Gas giants that orbit so close to their stars they complete a full year in just a few Earth days. Sometimes less, sometimes just hours. These planets shouldn't exist according to the models we built from our own solar system. Gas giants form far from their stars out in the cold regions, where it's cold enough for ice and gas to accumulate into massive spheres. Jupiter formed beyond the frost line. Saturn did too. They shouldn't be able to migrate inward through the inner solar system without being torn apart. And yet they do. We still don't fully understand the mechanics, gravitational interactions with other planets, friction with the protoplanetary disk. Something pushes them inward and they spiral toward their stars like water circling a drain. What we know is that these worlds are being cooked alive. Their atmospheres are boiling off into space, stripped away by stellar radiation and stellar wind. Some of them trail enormous tails of vaporized metal behind them, like comets. Sodium, magnesium, iron, elements that should be solid turned into glowing clouds, stretching millions of kilometers into space. One of these planets, WASP-12b, is so close to its star that tidal forces are stretching it into an egg shape. The star is eating it, slowly pulling material from the planet. Over millions of years, WASP-12b will be consumed entirely. Swallowed by its own sun, it's already begun. We can see the process happening in real time. Then there are the dark worlds. TRUS-2b is one of the darkest planets we've ever discovered. It reflects less than 1% of the light that hits it. Less than coal, less than asphalt, less than black acrylic paint. Darker than any material we've ever created on Earth, we don't fully understand why. Its atmosphere is thought to contain light-absorbing chemicals like vaporized sodium and potassium and titanium oxide. But the exact mechanism is still debated. The chemistry is complex, the temperature is extreme. What we do know is this: if you could see TRES 2b up close, it would be a black sphere faintly glowing red from its own internal heat. Like a dying ember floating in space, a ghost planet swallowing light and giving almost nothing back. It's the kind of thing that shouldn't feel ominous. It's just chemistry, just physics, just atoms absorbing photons. But it does. Some planets are hot beyond comprehension. Kelt 9b orbits a star hotter and brighter than our sun. The planet's day side to side, perpetually facing the star, reaches over 7,800 degrees Fahrenheit. Hotter than some small stars. Hot enough to vaporize iron. Hot enough that molecules in its atmosphere are torn apart into individual atoms. The planet doesn't have weather in any sense we would recognize. It has atomic rain, hydrogen atoms on the day side torn apart by heat, drifting to the night side where they cool and recombine into molecules, then circulating back to the day side to be torn apart again. It's hard to even call it an atmosphere. It's more like a shell of disintegrating matter held in place by gravity barely. The planet is losing mass. Every second, tons of material are being stripped away. Over millions of years, it will shrink. Maybe it will become something else entirely. Maybe it will vanish. And yet right now it persists. It orbits. It exists. Not all strange planets are hot. Some are unimaginably dense. There's a planet called 55 Cancri E. It's a super-Earth about twice the size of our planet. It orbits its star so closely that a year there lasts only 18 hours, less than one Earth day. Its surface temperature reaches 4,400 degrees Fahrenheit. The entire planet glows dull red from its own heat, but that's not what makes it strange. What makes it strange is its composition. Early observations suggested that up to a third of the planet's mass could be carbon. Not rock, not iron, carbon, compressed under immense pressure and heat into crystalline structures. Diamond A, Diamond Planet. The idea captured imaginations. A world where the mountains are diamond, where the crust glitters under alien starlight. Later studies have challenged this. The data is ambiguous. The models are uncertain, but even the possibility tells you something profound. It tells you that planets can be made of things we never considered, that carbon can dominate instead of silicon, that the periodic table offers more combinations than we ever imagined, that our classifications are incomplete. The universe is not limited by our materials. Then there are the rogue planets, worlds that don't orbit any star at all. They drift through the darkness of interstellar space completely alone, ejected from their birth systems by gravitational chaos. Three-body interactions, close encounters with other planets, or perhaps they formed in isolation, orphaned from the start, condensing from clouds of gas that never formed a star. We've detected dozens of them passing between us and distant stars. Brief shadows against the light. There may be billions more. Some models suggest there could be more rogue planets in the galaxy than there are stars. A hidden population of dark worlds wandering forever. Imagine a dark frozen world tumbling through the void for billions of years. No sun to warm it, no seasons, no day or night, just cold and silence, and the faint glow of distant galaxies' surface temperatures near absolute zero. Atmospheres frozen solid and collapsed onto the ground. Oceans, if they ever existed, locked in ice kilometers thick. And yet, even on these worlds, there could be warmth beneath the surface, radioactive decay in the core, tidal heating from a hidden moon orbiting in the darkness. Enough to melt ice into liquid water buried deep beneath a frozen crust. Entire oceans sealed away in eternal darkness, never touched by sunlight. We don't know if life could exist there. Chemistry in the dark powered by heat from below, but we can't rule it out. Some of the strangest planets are the ones that challenge our categories entirely. Brown dwarfs are objects too massive to be planets, but not massive enough to sustain hydrogen fusion, like a star. They glow faintly from residual heat left over from their formation. They have atmospheres. They have weather patterns, bands and storms like Jupiter. Are they failed stars or superplanets? The answer depends on how they formed, and nobody agrees on where the line is. There are worlds where the ground is made of water, ice compressed so hard it's as strong as granite, where the air, if you can call it that, is hydrogen and helium, where storms larger than Earth have raged for centuries without stopping, driven by heat from below. There are planets tidally locked to their stars, one side always facing the light, one side always in darkness. The day side scorched to thousands of degrees, the night side frozen. In between them, a thin band where temperatures might allow liquid water to exist, a ring of perpetual twilight circling the entire planet. We call this the Terminator Zone. Imagine standing on that boundary, the sun forever frozen on the horizon, neither rising nor setting. Behind you, endless night, before you, endless day, and you balanced on the knife edge between. There are planets orbiting binary stars, two suns in the sky rising and setting in complex patterns. Some planets orbit one star, while the other hangs distant in the sky. Others orbit both stars, tracing a figure 8 through space. The gravitational dynamics are chaotic. The orbits are unstable on astronomical timescales. And yet these planets survive sometimes for billions of years. There are super-Earths, rocky planets several times more massive than our own. Their gravity would crush you flat. You couldn't stand. You couldn't breathe. Your bones would fracture under your own weight. Their atmospheres could be thick enough to create a runaway greenhouse effect, turning the surface into a pressure cooker, or thin enough that solar radiation strips it bare, leaving nothing but rock and vacuum. We don't know what these worlds look like up close. We probably won't for decades, maybe centuries. Our telescopes can tell us they exist. They can tell us their size and mass and temperature, but they can't show us the surface, but we know they're there. Let me tell you about something called a chthonian planet. These are the leftover cores of gas giants, planets that once had thick atmospheres of hydrogen and helium, thousands of kilometers deep, but orbited so close to their stars that everything was stripped away by radiation and stellar wind. What remains is the naked core, rock and metal compressed under its own weight, glowing from the heat of its star, a planet reduced to its skeleton. One example is Kepler 70b. It orbits so close to its star that a year lasts less than 6 hours. The surface temperature is over 12,000 degrees Fahrenheit, hot enough that the rock itself might be vaporizing, slowly turning to gas. This is what happens when a planet dies slowly over billions of years. And then there are the ocean worlds. Not oceans like we have on Earth, shallow layers of water covering continents. Oceans hundreds of kilometers deep, thousands of kilometers deep, so deep that at the bottom the pressure transforms water into exotic forms of ice that only exist under extreme conditions. Ice 7, Ice 10, phases of ice that stay solid even at temperatures hundreds of degrees above the normal boiling point. Imagine diving into an ocean and descending deeper, past where light penetrates, past where any Earth creature could survive, down into darkness and pressure. And there is no seafloor, just more water, more pressure, more darkness. And then finally, thousands of kilometers down, you reach ice. But it's not cold. It's hot, compressed into solidity by the weight of the ocean above. And below that, a core of rock you will never reach. These worlds might be common, more common than Earth, like planets with their shallow oceans and exposed continents. And they raise an unsettling question. If life began in Earth's oceans, could it begin in oceans with no connection to a surface? No sunlight, no atmosphere above, no land, no tides, just water and darkness and chemistry. We don't know. The more we discover, the more we realize how limited our definitions really are. We used to think planets needed to be in the habitable zone, not too hot, not too cold. We used to think they needed a magnetic field to protect them from radiation. We used to think they needed to orbit a stable star. Now we know that life, if it exists out there, doesn't need our permission. It doesn't need our conditions. It just needs chemistry and time and energy. Every strange exoplanet we find is a reminder that we are not the center of anything, not the center of the solar system, not the center of the galaxy, not the center of the universe. Our ideas about what is normal or possible are not universal laws. They're local observations, temporary conclusions drawn from a sample size of 8 planets and 1 star. The universe has been running experiments for billions of years, building worlds under every possible condition, testing the limits of gravity and heat and pressure and time and chemistry. We are only now beginning to see the results, and what we've seen so far is this. The universe is far stranger than we imagine, far more creative, far more indifferent. It does not build worlds for us. It does not care if we understand them. It does not care if they offend our intuition. It simply builds, and we're left to look up at the sky and realize that everything we thought we knew about planets was based on a sample size so small it barely counts as data. We are newcomers here, visitors to a universe that has been forming worlds long before we existed and will continue long after we're gone. The planets we find are not anomalies. They are not mistakes. They are not rare accidents. They are the norm. And Earth, with its moderate temperature and liquid water and thin atmosphere in stable orbit, is the exception. The strange thing is not that the universe contains worlds of glass rain and vaporized metal and endless dark oceans. The strange thing is that it contains us